We were discussing in the last class is this admittance and impedance. This is basically in the AC circuit, because in DC circuit L and C, they have only effect in the very beginning when you switch on the circuit. I think that you have studied earlier, that whenever you switch on the circuit, the voltage takes time to develop across a capacitor. Okay, so that will grow exponentially for some time, but after some time in the long term, the voltage across the capacitor, the voltage across the inductor will become constant. Okay, so long term there is no effect of L and C. There will be no fluctuation, nothing. Okay, so L and C basically will have effect in AC circuit. They will offer impedance or admittance. Admittance is just the reciprocal of impedance. So they will offer admittance, impedance or admittance, or you can better say they will offer reactance, and reciprocal of reactance is called susceptance. Okay, and as a result, as we have seen mathematically in the last class, as a result of this reactance, the current and voltage in an RLC circuit where there is L or and or C, means there may be L, both L and C, or there may be only L or only C. Okay, so in a circuit where there is L and or C, in that type of circuit, the current and voltage generally they will be differing in phase. Differing in phase means that the waveform means, since it is AC circuit, your voltage will be written, you will be writing it as Vm cos omega t. Okay, so at any instant of time t, the corresponding current will be not exactly Im cos omega t. It will be cos omega t plus phi. That means if you see this, if you plot these two waveforms, the voltage and the current waveform in a circuit, in an RLC circuit, if you plot it, okay, or you can observe it on an oscilloscope. There is one instrument called oscilloscope, which you will be using it in your lab later on. So in oscilloscope, if you view the voltage and the current waveform, you will see that there is a difference in phase in these two waveforms. The two waveforms are not exactly going in the same phase. Whereas if it is a pure resistive circuit, there is no L, no C, only R, then you will see that the voltage and current, they are exactly in phase. That means whenever the voltage is going to its peak amplitude, current also goes to its peak amplitude, like that. Okay. So that effect we can, means how we can find out that what will be the phase difference and all these things. That is in a more convenient way we can do it by drawing phasors. Okay, so phasor, that is the usefulness of this phasor. Means using phasor you can do it. And then we have explained that how this impedance, what is this impedance, and how you can draw the phasor diagram corresponding to the impedance in the reactance due to L, reactance due to C, all these things we have seen in the last class. Okay, and then all these things we have discussed, that impedance will be having this real part resistance, imaginary part reactance, all these things we have discussed. So you can just read through all these things. I have posted these notes, handwritten notes, I have posted it. So you can read through all these things, and you can just work out on your own all these things, and then it will be clear to you. Okay. So we can just go through. These are all the things which we have discussed. Then regarding the power also, we have seen that there will be actually apparent power is Vi, but the actual power which is used, which you can utilize, is this Vi cos phi. Okay, and there is some reactance power Vi sin phi. Okay, so that is the reactance power which is actually not useful or used. Okay, it is the power which actually is delivered by your the source to the inductor and capacitor, and then in the other half of the cycle, that in the power or the energy again returns back to the source. So this power actually keeps on going from source to inductor, capacitor, and then again returns back. Okay, so like that, this reactance power is actually cannot be taken out from the circuit and used. Okay, whereas this is the power, actual power, which you use it for lighting your bulb, so it gets converted to light energy. You can use it in your heater to convert it to your heat energy. You can use this power to run a motor, so it is converted to mechanical energy. So this is the power which is actually from converted from your electrical power to some other power form, some other energy form. So this is actually which is taken out. You can take it out from your electrical system. Okay. So this is actually sometimes in some, mostly actually it happens that the the money that we pay, the money that we pay for our electric bill is mostly it is VI. That is something, yeah, because if you this reactor we are actually using VI cos phi, but you are paying for VI apparent power. So that is something which anyway we cannot do away with this. This is how the mostly the energy meter that you have at home for measuring the consumed power. It is mostly it measures is VI, not this VI cos phi. So you are paying for something which you are actually not using. Okay. Anyway, so that is something commercial thing. Okay. Uh, so these are the things. Then we have also talked about the admittance. This is the example. I have taken a simple example of a parallel RLC circuit, and we have discussed about this admittance. And then what I said that in admittance that the here the current will be constant. In the previous circuit, the voltage, applied voltage was constant. The applied voltage was constant, but I was changing in accordance to your R, L, and C. Okay, depending on the impedance value, your current will change. There it was a voltage source. The voltage was constant. Whereas here I am assuming, I am taking it like that, that IT is the current source. Okay, IT is the current source. So this is the circuit. IT delivers a constant current. So when the constant current is flowing through it, the current gets divided in three parallel paths. Okay, and the voltage Vt here, that will be, that will depend on your admittance. Okay, that will depend on your admittance. So that you can see here that your IRT is equal to 1 by RVT. Okay. Similarly, you have ILT, ICT. So these three currents, they should add up to give you your IT. Okay. IT is fixed. So that means the sum of the three currents, that is equal to your constant IT. So depending on your R, L, and C, your VT value should be adjusted. It will get adjusted such that the sum of these three currents is equal to your constant IT. Okay. So accordingly, we have seen in phasor diagram, we can check it from the phasor diagram that only in this case when your this omega L will be equal to 1 by omega C. That is the resonance condition. When this resonance condition takes place, okay, when omega L is equal to omega C, in that case, your output voltage V will be equal to I by G, because then in resonance, these two actually gets cancelled each other. They will cancel each other. So effectively, this parallel combination of this is like an open circuit. It is opened. Okay, they cancel each other, and effectively it is like that there is nothing here. So it is like an open circuit. Nothing means open. So you only have this R only. Okay, you are only having this R. So your V will be equal to your I into R. Or in other words, I would say that now my uh, I, since it is constant, the V shall be adjusted such that V by R is equal to your constant I. Okay. So that is what we were discussing in the last class. And then one question was raised regarding this voltage source and current source. What we mean by current source? You know voltage source. That is something which is common. You see every day in your day-to-day life, but current source you generally don't see. So that's why that question came in your mind. So I'll just go to the last two pages which I added today. Okay. So this is the voltage source. Okay. What we mean by voltage source? Voltage source is supplies constant voltage. So the current that will be given by the source will vary. It will change in accordance to the load. You can understand it. According to the Ohm's law, this I flowing in this circuit will be equal to V by ZL. So if your ZL keeps on changing, uh, depending on your load, your current will be changing. That is what actually you have at your home also. Okay, your the voltage that comes in the plug point. You have those plug points at your home where you plug in some any maybe heater or maybe some other device. You just at home you can plug in your table fan, you can plug in your heater, you can plug in something in the same plug. Okay, and depending on which load you are plugging in, the voltage there is constant. The voltage at your home is generally 230 volt, or sometimes we also consider it to be 220 volt. Okay, 220, 230, it's like that. Generally, it is 230 volt. That is the 230 RMS value of the AC voltage that you get at your home. 230 volt is the RMS value. Last class I have mentioned what is RMS. Okay. So at home you have RMS value equal to 230 volt, which is constant. So it is a constant voltage source. So depending on what you are plugging in, your current of flowing through that load will change. Okay, that is what it happens. Okay, so the current will vary. So you can always calculate the current that will be required because it is always, suppose I attach 1000-watt heater. You have at your home heater, it is rated, so 1000 ohm, like 1000 watt or something like that. Okay, so if you are plugging in a 1000-watt heater, your V is constant. So now you can calculate. Your required I will be I square R. I square R is equal to your 1000. Okay, that means V square by R is equal to 1000. V, you know, it is 230 volt. So you can calculate what is your R. Okay, you can calculate your R from there. V square is constant, 1000 watt. V square by R is equal to 1000. So you can calculate your R from there. And since you know your R, your I will be equal to V by R. Okay, so your I will be something. Now similarly, now instead of a heater, now if you plug in there a 100-watt bulb, okay, 100-watt bulb. So you can understand that here, whenever you are plugging in a 100-watt bulb, okay, then the current will be different. Okay, you can again calculate. Okay, the current, now the current will be different in a 100-watt bulb. So you can again calculate that V square by R will be equal to 100. So your R resistance will be basically here 10 times of that heater. Okay, because in heater it was V square by R was 1000. Now it is V square by R is equal to 100, a 100-watt bulb. So your R will be now 10 times more, and hence your current now will be 10 times less flowing through that bulb. Okay, so that is how all these calculations can be done, and you can find out what will be the current in different devices. So current basically keeps on changing, but your voltage is constant. So that is basically a voltage source. Now voltage source may be of two types. It is the DC source or the AC source. Okay, DC source, again, you know, battery cells. You have these battery cells that you put it in your torchlight and all these things, these battery cells, okay, that you get in the shop, the battery cells. Okay, even battery, the big batteries are there even in your many, that's for example in the car. The car is running, the battery that you have in the car, that is a battery cell. And you know that the voltage supplied by the battery cell, the constant voltage, that depends on the, you have studied in chemistry, that there is a electrochemical series. You have to calculate the EMF generated whenever there is a cathode, anode of two different elements. Okay, in the electrochemical series, we can find out what is their standard potential values, what is the difference in their standard potential values, and accordingly what will be the EMF generated due to the cathode and anode in that battery. And this you have done in your chemistry, in your class 12 chemistry, you have studied all these things, calculating EMF generated whenever there is a reaction between that is called some reduction oxidation will take place, redox reaction, and you will be having one cathode, one anode. So you can always find out what will be the potential that develops across the cathode and anode. For example, the battery, the Lakeland cell that we buy it in the market, they have 1.5 volt fixed all over the world because it is using a fixed chemical. The elements used is fixed. That is used everywhere, the same element, and hence it will always give you 1.5 volt across its terminal. Okay. So that is that type of DC sources you have. Okay. You have also studied DC generator. This also you have studied in your physics. Okay. And this in DC generator, the voltage is developed due to the Faraday's law. Okay. What you have some north-south two poles. So there will be a magnetic flux between these two poles, and there will be a conductor like this, which will be rotating conductor like this. And whenever this conductor rotates, it cuts the magnetic flux. Okay, it cuts the magnetic flux. This magnetic flux is fixed, but since it is rotating, it will keep on cut the magnetic flux that is that passes through this area of this magnetic conductor, that keeps on varying, and accordingly you have a defined voltage that is induced, voltage induced in this conductor, and you generate the voltage. Okay, that is how the generate EMF is generated. Okay, so that you have studied, and in fact this details we are not going into that. You have the basic things you have studied in your higher secondary level. Okay, in electrical, I don't know whether you are studying it in electrical science or not. In electrical engineering, they teach DC generator, because actually DC generator, this is the basis of the DC generator, but it is not the DC generator. DC generator will have this type of conductors, many conductors, and that conductors, they will be on a rotating rotor. It is called rotor. On that rotor, there will be many conductors. Okay, and there will be many poles like this. There will be many pairs of poles, many pairs of north-south poles surrounding it. So when that rotor rotates, the conductors, they will be developing the induced current, not only due to just one magnetic field, but there are many magnetic fields, okay, crossing this, many magnetic fields. So there will be this rotor will be rotating, all the conductors will be generating the EMF, induced EMF, and they are added up. All these EMFs, total EMF will be added up in all the conductors. So it's like one after the other, all the batteries are connected. It's like that. Okay. And accordingly, this is the voltage that is generated in a DC generator. Okay. This is a DC generator that generates the voltage, and this is the voltage equation. So we are not going into details of all these things. This generally in electrical engineering you study that how electricity is generated in a DC generator. So you can see that V will be fixed because N is the RPM, rotation per meter, which is generally taken to be fixed. So obviously V will be fixed. P is the number of pole pairs, number of pole pairs. I said there will be many pole pairs like this. So P is the number of pole pairs. So that is fixed. Okay. The pole pair, these pole pairs will be having a constant magnetic flux. They will develop a constant magnetic flux. So phi is constant. Z is the number of conductors on that rotor. Here I have shown only two conductors, one going this way and one coming this way. But like that you have many conductors. Okay. Z is the number of conductors and A is equal to P in case of lap winding. There are two types of winding, lap winding, and A is equal to 2 in case of wave winding. It's like, okay. So these are the two types of DC sources, battery cells, which is based on the chemical reaction, and DC generator, which is based on your Faraday's law. AC source is the same thing. In AC source, you have the same thing like this. Only thing here you have a commutator. I think you have studied that. That in commutator, what it will do, actually when this conductor is rotating, the current will be flowing in one direction for half the cycle, and then in the other half of the rotation, the current will be flowing in the opposite direction. And in DC generator, there is a commutator which will then reverse the current direction in such a way that you get the current in one direction finally. Okay, that commutator is taken out. If you take out that commutator, then it becomes basically an AC generator. The current will be flowing in one direction in one half of the rotation, and current will be flowing in the other half of the rotation. So it becomes an AC source. So the same principle of Faraday's law, but without using the commutator. That commutator is not used. So the current is not deliberately made unidirectional. Here, using the commutator, you make the current deliberately unidirectional. Okay, that is the difference. There is another type of AC source which is called alternator, synchronous generator or alternator. There it is actually just the opposite. Here you have the magnets are fixed, the conductors are rotating. Okay, and there it is just the opposite. The conductors are kept all around, and the magnetic, there will be a magnetic rotor which will be rotating. So the magnetic field is rotating, cutting the conductors. Here actually the magnetic field is fixed and your conductor is moving and cutting that magnetic field. Okay, whereas there the conductors, the position of the conductors are fixed, but the magnetic field is rotating. So it's basically the relative motion remains the same. It's basically just the relative motion is same. There should be a relative motion between the conductor and the magnetic field, and that is maintained. Only thing you have changed which one to be rotated and which one not to be rotated. That's all. So these are basically the voltage sources, whereas the current source is where I have to supply constant current. Now how we do it? So for that we have an electronic circuit. We use one electronic circuit, because see, all these things which you are seeing daily in your daily life, which can be built using our chemistry, using our physics, whichever source we can build, they are all voltage sources. So now what we can do, we can convert this voltage source to a current source. How? By using an electronic circuit, okay, which will do voltage to current conversion. Okay, so the current will be proportional to the voltage in such a way that if your voltage source is supplying constant voltage, the output will be also constant current. Okay, that is what we want. So that output, now I can say this is my current source. Okay, how? I am showing one example that I have one constant voltage source. As we have discussed above, we have one constant voltage source supplying constant voltage. This is an op amp. I think you have already studied op amp in your electronic part. Some basic your idea you are having. Okay, so this is the op amp and we are making a circuit like this. The load is connected here. So basically up to this it is the source, current source. Okay, this is the current source part. Voltage source, and you have one simple op amp connected to it with one resistance like this. Okay, so this is your load connected to the current source. This is how you make it. It's a simple one, simple just for your understanding. This is a simple current source. Okay, voltage source, constant voltage source is basically converted to a constant current source. How? Now you know, means you might have studied already, that when in an op amp, we always consider that whatever the voltage is here, the same voltage also is present at the other terminal. The voltage, because the voltage difference between the two terminals must be equal to 0. That means they should be, the applied difference voltage should be equal to 0, so that the output is finite. If there is a slight difference in the input voltage, the output will become infinite. Okay, so to maintain a finite output voltage, we use a feedback. Here the feedback is through the load. Okay, we use a feedback path. Okay, and whenever there is a feedback, the output becomes finite. Okay, output becomes finite because of the negative feedback. Output becomes finite, and whenever the output is finite, essentially it means your input is now equal to 0. If your input is equal to 0, then whatever the voltage is applied at this point, the same voltage is applied at the other terminal. Okay, so here we can consider that virtually, this is actually virtually the same voltage. Okay, so since virtually they are in the same potential, I can consider that this voltage is Vs, and hence the current flowing through this resistance is Vs by R, because this R is grounded. This is Vs, so this I is equal to Vs by R. Since Vs is constant, Vs by and R is a fixed resistance I am using, so I is also constant. Okay, so now you see, you must have also studied that the current actually does not flow through the op amp. Okay, no current will enter because it's a high impedance input terminal. No current essentially enters an ideal op amp. Okay, so whatever current is flowing through this, that current must be coming from here. That is the only place from where it can come. Okay, because there is no other current flowing from this Vs2 inside the op amp. Okay, so there is no current in this part. There is no current. So current is not flowing from Vs to this like this. No current. Okay, so current must be coming only from the op amp through the ZL and then going to R. So this current is also equal to I. Okay, so obviously everything is considered to be of ideal, and hence we are making all this. Yeah, it's a simple circuit. So there might be the op amp, if it is non-ideal, then obviously you have to go for some other compensation to make it a perfect constant current source. But it's a simple circuit I am showing you for as an example. Okay, so this is how a constant current can be generated, and that can be used as a constant current source. That is what current source means. Okay, one thing noted, that in AC, voltage or current is constant means that we are considering that RMS or the amplitude, you can say, because RMS is nothing but amplitude divided by √2. So RMS is constant. We are considering that the instantaneous value in AC current or AC voltage, instantaneous value is not constant. That will keep on changing in sign, cos, like that. Okay, that will keep on changing. But what we mean by constant means basically it is the constant RMS. In fact, in our phasor diagram, we are considering that RMS. Okay, that is constant. And this is what actually in the phasor diagram that we have shown earlier. Your load is basically this. So this is your 1 by ZL. You know that parallel circuit, how to calculate the impedance. So accordingly, you can calculate your V. The V will come out to be this. This is what we have done. Okay. Okay. Just one thing, something which I have not written here, means I have missed it. These are what I am showing here. This V. This V is actually ideal. Okay. That means whatever the voltage we are considering generated here, that voltage is also appearing at the terminals. Okay. But actually, we don't get it. Okay. For example, the battery, as I said, when you go to the market, you buy it, it is written 1.5 volt. But if you check after opening that battery, if you put one voltmeter across the battery and if you check the voltage, you will see that it is actually not 1.5. It may be 1.4, 1.45, like that. Some slight difference is there. Okay. And that difference is basically, practically, there will be some resistance inside the battery. Inside the battery, there will be some resistance offered by the chemicals and all these things that is there. Even the contact will also give you, you know that there is a nice pin like ND, means that contact where you make the contacts. Okay, so that contact will also offer some slight resistance. So all those resistance actually in a practical source, you will have all those internal resistance. So they are called source resistance or internal resistance. In a voltage source, we model that. So we don't know exactly where that, because it's that resistance is just scattered inside the whole battery. It is scattered everywhere. We are just modeling it, and we want to, when we draw the circuit, we want to put it somewhere in the along with this source. Along with the source, we want to draw it just to show that there is some drop due to that resistance. Okay. So that resistance, when we model it in a voltage source, you have to put that R in series with this, because you know that since current is flowing through this, if I put that R in series, then I will say that the actual voltage appearing across the terminal will be V minus I into source resistance. Okay. So that's why you put it in series. Whereas in a current, you can understand that the same source resistance, we just model it by putting it in parallel to it. That means it will give you a leakage path. So some current will be leaked through that source resistance. Although it is supposed to give you a constant I, but actually you get some current which is less than I, and that is modeled by taking one parallel path here, showing that this path gives you the source resistance through which the current leaks inside the source. Okay, that's all. It's just because in future you will be, when you will be drawing the electrical circuit, you have to sometimes you have to also include the source resistance. So in a source resistance, in current source, the source resistance will come in parallel, and in voltage source, the source resistance we consider it to be as if it is in series, as if. Okay. In ideal case, source resistance is taken to be 0. In voltage source, source resistance is taken to be 0, whereas in ideal current source, source resistance is taken to be infinite. Infinite source resistance, ideal case. Okay, just keep it in. Okay, so that is about the current source and all these things we have discussed. So we just go through it once more. Now another question was raised, why we are preferring AC, okay, over DC? Because when I was saying that when omega is large, then you have problem in transmitting radio waves. Okay, then someone pointed out, then if so, then why we don't use DC? Okay, because in that case your frequency is 0, so there will be no effect of L and C, so that will be fine. Okay, the first I want to first I will discuss that why we prefer AC, okay, for power transmission. At home, why we are not using DC, why we are using AC, okay. I think to some extent you have studied it in your class 12 CBSE book. I have seen it. It is there, okay. I have a voltage. Okay, I am considering that it is a voltage, constant voltage source that is the generally that you have at home as well as everywhere. Everywhere you will see that it is a constant voltage source. Okay, so current source is used only in where it is required in some special cases. Okay, it's not that in general at home we use it. Okay, so in general at home or in industry, even in industry also, mostly what we use is constant voltage source. So we are considering it to be a constant voltage source, and there is some load RL connected somewhere, means I have to run this load. Okay, so accordingly there will be some power. That power is rated, PL is rated. Okay, this, as I said, it is, suppose if it is a heater, it will be rated that 1000 watt. If it is a bulb, it is rated as 40 watt, 60 watt, 100 watt, like that. So the power is rated. Okay, and accordingly you can see that power PL will be equal to whatever the current is flowing through it. Current is set through the whole circuit, I square RL, or I can say this is equal to VL into I. But what is VL? VL is V minus IR, where R is the resistance due to the long conductor. I am considering that this conductor is non-ideal. Even if it is a copper wire, it offers some resistance, and it is more prominent, this resistance, if you are transmitting the power from from a grid station, like from one city to another city, you are transmitting the power. From city to the village, you are transmitting the power. So obviously your conductor will be very large. So that even if it is a copper, even if it is aluminum, it will offer some resistance. So your VL, the load at this point, the voltage at this point will be equal to V minus IR. I am considering this R total resistance of the conductor. So total resistance of the conductor drop will be IR. So V minus IR into I. So that will be the power PL. Okay. So what is the power loss? So how much power I am losing? I am losing this much of power. PL square by VL square. PL by VL is what? PL by VL is your I. Okay. PL by VL is your I. So that you can see that I is equal to PL by VL. So PL square by VL square is your I square R. Okay, so this is equal to this. This is the power loss. I square R. I is same in the whole circuit. So I square and R is the resistance of the conductor. So this is the power loss. This we should try to minimize. We don't want the power to be lost in the way of transmission. Okay. So in order to lower down this loss, I will like to have this I as small as possible. Okay, because R you don't have any control. This is, if you are having long distance transmission, obviously R will be more and more. You don't have any control over it. You can make your conductor better and better, but that will again you have to, if you use copper wire, for example, instead of aluminum wire, then that will be costly. So that is another problem. So given the conductor already laid down, okay, so using that conductor with the particular R already known to you, what I can do that in order to reduce my power, I can go for lowering I. That is the only way I can do it. Okay. So if I want to lower down my I, then this is the only way. What is my I? I is equal to PL by VL. I is equal to PL by VL. And PL, as I said, that the load is fixed. I can say that more or less the load is fixed, that that in a particular house or in a particular area, this is the total load that will be used. Obviously, that load keeps on changing, but actually there is an average load that is always calculated. Depending on that only, all the electrical distribution system in a city is actually designed. That what is the average load. So whenever there is some new building, you always do some load testing. It is called load testing. We have to do some load testing. We have to see that how much load it is consuming. All those things are there. That is all something to do with the electrical engineers. Okay. So here, considering that the PL is fixed in a given house or given city, PL is fixed. In order to lower down my I, the only way I can do it is now increasing VL. Okay. Now, as I have said, what is VL? VL is V minus IR. Okay. Now, when I am trying to reduce my I, then obviously V minus IR, this IR will be smaller and smaller. So V will be almost coming down equal to VL. Okay. So you can see it is just how I am doing it. That now, that means in order to increase my VL, I will increase my V. Okay, I have to increase my V. So if I increase my V, if I go for a very high voltage transmission, that is called high tension transmission actually. If I go for high voltage transmission, then you have this I smaller. Okay, ultimately you can see that your I will be smaller, and then your IR square loss, this loss in the transmission part will be smaller. Okay, but the problem is that if V is large, then VL is also large. Now if VL is large, it is dangerous. If you're at your home, if you have, suppose I am sending here, the voltage here is 11,000 volt, your VL will be also almost equal to 11,000 volt. And if that is the voltage at your home, then that is dangerous. Okay, we cannot go for that, because that it will be fatal. Okay, so what we will like to have is that we like to step down the voltage when ultimately it comes to our home. So you see the thing, we want high voltage transmission from the generating station, high voltage transmission, but at my home I want very small voltage, and that is possible only in AC transmission. Only in AC transmission that is possible, because there is something, a machine, an AC machine called transformer, which can do it without loss of any power. There will be some loss of power in the transformer, but that anyway, that is a negligible loss. Okay. Otherwise, ideal transformer will transmit the whole power from one. You can see this is the transformer, how it is symbolically represented. The total power from this side is passed on to the other side of the transformer. Okay. So that is how the transformer can help you in doing power transmission from one side to the other side, but the voltage can be stepped down. The voltage can be stepped down, and that stepping down of the voltage will depend on the turns ratio. There are some turns. Okay, this transformer, I don't know whether you have seen it. There are some windings on this transformer. There will be some conductor windings will be there. So depending on the windings, number of windings on this side and number of windings on the other side, okay, that voltage will be stepped down. So for example, if it is 10:1, if the turns ratio, then the voltage will also get stepped down by 10 times. Okay. So you see that I need power PL here. So I need V2 into I2. So I2 should be like something like this, flowing here. Okay. which is equal to your now V1 into I1, the same power on the two sides. So the same power V1 I1 passed on to this side becomes V2 I2, and that V2 I2 is your PI. Okay. Now V1 I1 V1 is very large compared to V2. I1 will be very small compared to I2 because they are same. Okay. But I have this R. So here the current is now more. Here the current is less. Okay. So here there will be less drop, ohmic drop, less power loss, I square R. But here I2 is large, but it is only at home. Only this one is only at my local circuit. So the total resistance here will be very small. Here the R is very large because it is a long distance transmission. So long distance transmission, I make V1 large, I1 small. Local circuit, I make V2 small, I2 large. So R is very small here. So ultimately my power loss in this local circuit will remain negligible. It will be not much. Okay. This you cannot do in AC. This type of transformation of power from one side to another side without any loss of power, that you cannot do in DC. It is only possible in AC. That's why we go for AC circuit. You must have seen it that in your at your home, near to your home somewhere, you must have seen on the roadside there will be a transformer. You must have seen it, and it is written there 11 kV danger, something like that. So there it is done like this, that 11 kV is coming to your locality by high tension line, and then in your local transformer is stepping it down to 220 volt or 230 volt, and then sending it to your home. Okay, that is how AC is helpful. Okay, that is how AC is helpful. However, the question was that then why we are actually so DC we are discarding. So no DC. So now it is AC. Now when it comes to AC, power transmission, we don't go for high omega. Power transmission is done at 50 hertz or 60 hertz. In some countries it is 60 hertz, in some countries it is 50 hertz. Okay. So DC we will not go, AC will go, but in AC we will try to do power transmission, power line transmission. That we will go for lower frequency. That's why we don't go for high frequency. We go for only 50 hertz or 60 hertz. Because otherwise this L and C will have large effect in power transmission. That we don't do. Okay. But in electromagnetic wave, there is, we can go for lower frequency, but the problem is that electromagnetic waves are, as we will see later on, that for transmission of electromagnetic waves to carry messages, for example, audio, we cannot go for lower frequency. Why? Because our audio itself is up to 20 kilohertz. So how can you make it smaller? Cannot make it smaller. Okay. In fact, we make it larger. The omega is made larger. Okay. Because of some reason that we will study afterwards, that why something called frequency division multiplexing. For that, we have to in fact increase the frequency. Okay. So transmission frequency is in fact increased. You cannot go to 50 hertz or 60 hertz because our voice, video, all these signals which we have to send, all the signals itself are high frequency. You cannot make them smaller. Rather, we actually make them, we increase the frequency. We increase the transmission frequency for some reason, which is called frequency division multiplexing, which we will study afterwards. Okay. So that is actually the problem with the transmission line. That in transmission line, we can only go for this message transmission, this electromagnetic wave, this message transmission using electromagnetic wave. We can use transmission line only at lower frequency. Higher frequency, it is not good. So for higher frequency, we have to go for waveguide or maybe wireless. Okay, we have to go for wireless transmission. Transmission line is good for only smaller frequency, which you can see here. Okay, I think it's already 5:58, so we'll continue next class. Okay, next class I'll complete this one and then complete the waveguide section. Okay, so I think up to this we have discussed today. So we'll continue from here. I have uploaded all these things already. You can go through all these things. Okay. Any question, Bolo? If you have any question, then you can ask me, uh, which I'll try to answer today or maybe tomorrow, right? Next day. Else, if you don't have any question, then you can start leaving the meeting.
Thank you, sir.
Okay, bye,
Thank
all
you.
of you.
Thank you,
Thank you,
sir.
sir.